Number 1. Cerro Blanco, Argentina. High in the Andes of northern Argentina, 4,700 meters above the sea, there is a place where almost nothing lives. The wind cuts at the skin. The air carries less than half the oxygen your body wants. The ground is rust orange and gray, scattered with frost-broken rocks stretching toward a horizon of jagged white peaks. And in the middle of this freezing plateau, there is a circular basin sunken into the earth. 6 kilometers across, ringed by pale cliffs that look from a distance like fresh snow. Almost no one comes here. There is no road that reaches it. There is no town within 50 kilometers. There are no monitoring stations on its rim. And 4,200 years ago, this hole in the ground threw approximately 110 cubic kilometers of pulverized rock into the sky, devastated everything within 1,000 kilometers, and may have helped collapse 3 of the earliest civilizations on Earth. To understand what 110 cubic kilometers of pyroclastic material means, picture the eruption of Mount Pinatubo in the Philippines in 1991. Pinatubo killed hundreds, displaced hundreds of thousands, and put a measurable dent in global temperatures for 2 years. Pinatubo erupted approximately 10 cubic kilometers of material. Cerro Blanco erupted more than 10 times that volume. On the standard volcano scale, the Volcanic Explosivity Index, or VEI, this places Cerro Blanco firmly at Category 7. 7 on a scale that only reaches 8. The kind of eruption that happens only a handful of times in 100,000 years, the kind that changes the climate of the entire planet. The Argentine geologist José Viramonte first characterized the deposit in the 1990s. His student, Walter Baez, refined the dating and the volume estimates in 2015 and 2020. Tephra from the eruption has been identified in seafloor sediment cores in the Atlantic Ocean, more than 1,200 kilometers downwind. Inland, the Atene ignimbrite, a related deposit, blankets thousands of square kilometers of the Altiplano Puni with a pale, welded layer of tuff. Walk across that tuff today and you are walking on the ash of a single afternoon 4,200 years ago. The timing matters. 4,200 years before the present is exactly the moment archaeologists call the 4.2 kiloyear event. Across the planet, the climate dried out. The Egyptian Old Kingdom collapsed. The Akkadian Empire in Mesopotamia fell apart. The Indus Valley cities depopulated. The American archaeologist Harvey Weiss has argued that this aridification was driven, at least in part, by volcanic forcing. Cerro Blanco is one of the candidate volcanoes responsible. The link is contested, but the timing is not coincidence on a scale anyone can dismiss casually. What makes Cerro Blanco a dormant supervolcano rather than an extinct one is what is happening to it right now. The American geophysicists Matthew Pritchard and Mark Simons, working with satellite radar interferometry, a technique called INSAR, discovered in 2002 that the entire caldera is sinking slowly, approximately 1 to 2 centimeters per year. That subsidence is not the signature of a dead volcano. It is the signature of a still present magma chamber, somewhere between 5 and 10 kilometers beneath the surface, slowly cooling and contracting. A magma chamber that taps into one of the largest reservoirs of partially molten rock anywhere on the planet, the Altiplano Puna magma body, estimated at 500,000 cubic kilometers in total volume. 3 views compete on what happens next. The mainstream geological view treats Cerro Blanco as effectively extinct, slowly cooling, with a recurrence interval too long to worry about within a human lifetime. A second view, held by the active research community working in the Puna, treats Cerro Blanco as dormant, its magma reservoir still replenishable, its eruption clock not yet stopped. A third view, held by a smaller group of Argentine geologists, points to anomalous gas readings and isolated thermal signatures suggesting that recharge may already be underway. The Argentine National Geological Survey, SEGAMAR, monitors the volcano. But the seismic network on the Puna is sparse. A precursor swarm could begin and continue for hours or days before anyone outside the Andes noticed. From the most isolated supervolcano on Earth, we move to the most actively monitored and the most actively growing. Number 2, the Kikai caldera, Japan. 50 kilometers south of the Japanese island of Kyushu, beneath the surface of the East China Sea, there is a circular basin in the seafloor. 19 kilometers across, mostly invisible from above except for two small islands that mark the rim, Iwo Jima and Takashima. Tourist boats from Kagoshima sometimes pass overhead. The fishermen of southern Kyushu work this water every day. And on the floor of that submerged basin, 200 meters beneath the waves, a lava dome is growing, not slowly, continuously. It is now 10 kilometers across and 600 meters tall. It contains approximately 32 cubic kilometers of dacitic magma, and it is being fed by a chamber that is, by every available measurement, actively pressurizing. 7,300 years ago, this caldera produced what is called the Akahoya eruption, the most recent confirmed VEI-7 super eruption in human history. Approximately 170 cubic kilometers of tephra, pyroclastic flows so dense and so fast they crossed more than 100 kilometers of open ocean and reached the southern coast of Kyushu, where they obliterated the early Jomon culture living there. The archaeological record shows that human populations on southern Kyushu took roughly 1,000 years to recover. Not 1 century, 10 centuries. The Keiya ash layer left by the Akahoya event is so distinct that Japanese archaeologists use it as a stratigraphic time marker. Anything below it predates 5300 BCE. The lava dome was discovered and mapped by the Ocean Bottom Exploration Center at Kobe University, led by the geophysicist Yoshiyuki Tatsumi. In 2018, Tatsumi and his colleagues published a paper in the journal Scientific Reports confirming that the dome is being supplied by a magma chamber chemically distinct from the post-Akahoya products. In plain terms, the magma feeding the dome is not the same magma left over from the last eruption. It is fresh, recently arrived from depth, and chemically different in ways that imply a new pulse of recharge. A 2024 follow-up study refined the growth model and warned, in unusually direct language for a peer-reviewed paper, of the system's capacity for renewed VEI-7 activity. Tatsumi's group has modeled what would happen if such an eruption occurred today. Approximately 100 million people in southern Japan live within potential ashfall and pyroclastic effect zones. Stratospheric sulfur injection would produce multi-year global cooling. Agricultural systems across the northern hemisphere would face severe stress. The 2022 Hungatonga eruption in the South Pacific, a smaller VEI-5 event, has been used as a partial analog for the early phases of a Kikai reactivation. Hungatonga produced a sonic boom audible across the Pacific. It triggered tsunamis that killed people in Peru. And it was several orders of magnitude smaller than what Kikai is now capable of producing. The published probability estimate for a VEI-7 event from Kikai in any given century sits at approximately 1%. 1% sounds reassuringly low, but the consequences of that 1% are civilization scale. The volcanologist Nobukazu Siyama, also of Kobe University, has stated publicly that Kikai is, in his judgment, the most likely site for the next super eruption on Earth. 3 views run through the literature. The mainstream view treats 1% per century as the working estimate, which translates to slow recharge and a low decadal probability of eruption. A second view, held by Tatsumi and Siyama, holds that the system is actively pressurizing and that evacuation planning for southern Japan should be a national priority. A third view, more cautious about extrapolation, points to Hungatonga and argues that submarine systems can detonate without the kind of sustained seismic warning we expect from continental volcanoes. From Japan's most dangerous volcano, we move to America's most overlooked. Number 3, the Aniakchak caldera, Alaska, United States. On the Alaska Peninsula, halfway between Anchorage and the Aleutian Islands, there is a perfectly circular basin in the tundra, 10 kilometers across, 500 to 1,000 meters deep, ringed by jagged gray-brown cliffs. Inside the basin, a turquoise lake, a small symmetrical cinder cone, and almost nothing else. The land around it is treeless, mossy green and rust orange, scoured by Pacific weather. There are no roads. There is no town. The administrative status of the place is Aniakchak National Monument and Preserve, one of the least visited units of the United States National Park System. Fewer than 100 people set foot on the caldera floor in any given year. 3,430 years ago, approximately 1,650 BCE, This volcano produced a VEI6 eruption and ejected approximately 50 cubic kilometers of tephra. The ash layer, called Aniakchak 2, has been identified in the GISP2 ice core from Greenland. For decades, the sulfate signal from this eruption was confused in the paleoclimate literature with the Thera eruption that destroyed Bronze Age Crete. Geochemical fingerprinting eventually separated them. The Aniakchak 2 event coincides almost exactly with the abrupt cooling that disrupted the late Bronze Age Eastern Mediterranean. Some paleoclimatologists now argue that part of the climate signal once attributed to Thera should be reassigned to the Alaskan caldera. A volcano on the other side of the planet may have helped end an empire on the Aegean. After the caldera collapsed, smaller cones built up inside it vent Mountain, the half cone, testifying to continued activity. Surprise Lake, on the southeastern caldera floor, drained catastrophically through the Aniakchak River roughly 1,900 years ago. A wall in the rim gave way. The lake emptied in days. The flood scoured the river valley and reshaped the coastline. The most recent magmatic event was on the 1st of May, 1931. A vent inside the caldera ejected 0.4 cubic kilometers of tephra. The eruption was witnessed and documented by a Jesuit priest, Father Bernard Hubbard, known as the Glacier Priest. Hubbard's photographs and writings describe what he saw as, in his own words, a Mars on Earth. Black ash, smoking vents, no vegetation, no life. The volcano is monitored by the Alaska Volcano Observatory. But the instrumentation is extremely sparse because the caldera is so remote and the logistics so difficult. Tom Miller and Robert Smith, two of the senior Aniakchak researchers, have documented persistent low-level seismic activity beneath the caldera floor. Sockeye salmon spawn in Surprise Lake every summer, despite the lake's post-volcanic chemistry. A single bald eagle circling overhead in a basin where the silence is broken only by wind. 3 views again. The mainstream view is that Aniakchak's long quiescence between major eruptions implies a low immediate risk. A second view, the clustering model, holds that Aniakchak's eruptions arrive in bunches separated by long quiet periods, and that the next event could begin with very little precursor warning. A third view, held by some Alaskan geologists, argues that the 1931 eruption was the start of a new active phase rather than its end. From the supervolcano almost no one watches, we move to the supervolcano with 6 million people living on top of it. Number 4. The Macolod Corridor and Bombon Caldera, Philippines. In southern Luzon, 60 kilometers south of Manila, there's a famous postcard, a small island in a lake. The island has a smaller crater on it. Inside the crater is another smaller lake. The local tourism literature calls it an island in a lake on an island in a lake on an island. The island in the central lake is Taal Volcano. It is one of the most famous active volcanoes in the world, and it is the smallest visible feature in a much larger system that almost no one outside Filipino volcanology has ever heard of. The Bombon Caldera is 25 kilometers by 30 kilometers. The Macolod Corridor, the larger volcanic zone that contains it, runs 30 kilometers wide across the southwest of Luzon, from Bombon through Mount Macolud to the Mount Malapuno complex. The corridor was formed by multiple Pleistocene super eruptions, the largest of which produced an estimated 100 to over 500 cubic kilometers of pyroclastic material, VEI7 class. The tall tuff deposited by these events is mapped across central Luzon. Tectonically, the system sits above the subducting Philippine Sea Plate, which is being driven beneath the Eurasian Plate at approximately 9 centimeters per year, among the fastest convergence rates anywhere on the planet. Taal itself has erupted 35 documented times since 1572. The 1754 eruption lasted 7 months. The 1911 eruption killed approximately 1,335 people in a single base surge of superheated ash. And on the 12th of January 2020, Taal produced a 14-kilometer ash plume, displaced more than 376,000 people, and at peak emitted over 14,000 tons of sulfur dioxide every day. The unrest continued through 2021 and 2022. The Philippine Institute of Volcanology and Seismology, PHIVOLCS, under its director Renato Solidum, formally reclassified TAL's threat assessment to include caldera-scale eruption scenarios. Recent geothermal modeling by the University of the Philippines and the United States Geological Survey has identified a magma chamber beneath the Bombon caldera, at depths between 5 and 15 kilometers, with an estimated volume of several hundred cubic kilometers. The corridor's heat flow is so high that it sustains the Tiwi and Macbon geothermal power plants, providing a significant fraction of Luzon's electricity. The same heat that could devastate the region keeps its lights on. Manila, with its 13 million inhabitants, sits 60 kilometers north. 6 million people live within 30 kilometers of TAL. By any measure, this is one of the most densely populated supervolcanic zones on Earth. 3 views run through the modern literature. The mainstream view, until recently, treated TAL as a stratovolcano and Bombon as a dormant caldera that was unlikely to reactivate at full scale. The FIVOLC's revised view, post-2020, treats the corridor as one integrated system capable of caldera-scale activity, with the broader plumbing demonstrably alive. A more cautious fringe view holds that the 2020 unrest was the beginning of a recharge episode that could culminate in a VEI-7 event within a human generation. From a tropical caldera under millions, we move to a Mediterranean island under tourists. Number 5. The Ischia caldera, Italy. In the Bay of Naples, 30 kilometers west of the city, there is a small volcanic island called Ischia. The island is 46 square kilometers in area. About 60,000 people live there year-round. In summer, the population doubles because Ischia is a holiday destination known for its hot springs, its terraced hillsides, its Roman ruins, its luxury spas. Tourists fly in from across Europe to bathe in the thermal pools and walk the old fishing villages. The volcanologists who work in the region call Ischia a resurgent caldera. Every visitor to the island is standing on the post-collapse uplift of a Pleistocene super eruption. The defining event was the Monte Epomeo green tuff eruption, dated to approximately 55,000 years ago. Volume estimates range from 35 to over 60 cubic kilometers of pyroclastic material. The high end of the range puts it at low VEI-7. The eruption produced welded tuffs that now form the bulk of Monte Epomeo, the island's central peak at 789 meters elevation. After the eruption, the caldera floor began to lift. In the past 33,000 years, Monte Epomeo has been pushed up approximately 800 meters, among the highest documented rates of resurgence anywhere on Earth. The geophysicists Stefano Carlino and Roberto Castaldi have modeled the underlying magma body. It sits at 2 to 5 kilometers beneath the surface. Ischia has erupted multiple times in the historical period. The most recent magmatic event was in 1302 of the Common Era, the Arso lava flow on the eastern part of the island, which forced the evacuation of the medieval town of Gironda. The hot springs that anchor the island's economy are surface expressions of this still active hydrothermal system. The water at the spas of Cos-Nisyros, Forio, and Laco Meniu is being heated by a magma body that is, geologically speaking, actively present. On the 21st of August 2017, an earthquake of magnitude 4.0, with some estimates higher, struck the town of Cos-Nisyros, Terme. 2 people were killed, hundreds of buildings were damaged. The earthquake was driven by shallow caldera-related faulting, not by deep tectonic stress. The volcanic system was the source. Giovanni Orsi and Mauro Di Vito of the Vesuvius Observatory, the regional branch of the Italian National Institute of Geophysics and Volcanology, have argued for years that Ischia's eruption hazard is underappreciated relative to its more famous neighbor, Campi Flegrei. The Italian Civil Protection Service maintains an emergency plan for the island. Critics of that plan argue that it assumes gradual escalation rather than sudden eruption. The hydrothermal water chemistry tells the same story. Elevated CO2. Helium-3 isotope ratios characteristic of mantle degassing. The green tuff tephra has been identified across central and southern Italy, into the Adriatic, in cores off the Croatian coast. The seismic record on Ischia stretches back to Roman accounts and is one of the longest historical earthquake series for any small island in Europe. The Italian word Casamicolare, derived from the name of the town devastated repeatedly by earthquakes, once meant simply to be devastated. 3 views again. The mainstream view treats Ischia as post-caldera quiescent, with intermittent low-level activity but low caldera scale risk. The Orsi and DeVito view holds that Ischia's hazard is systematically underestimated and that VEI 6 or 7 reactivation is plausible within centuries. A third view, more speculative, treats the 2017 earthquake as the start of an unrest cycle, with eruption possible within decades. From the Mediterranean to the Pacific, and the most rapidly uplifting caldera on Earth. Number 6. Ioto, formerly known as Iwo Jima, Japan. There is a photograph almost every American has seen. 6 United States Marines raising a flag on a rocky hilltop. The hilltop is Mount Suribachi. The date is the 23rd of February 1945. The photographer is Joe Rosenthal. The image won the Pulitzer Prize. It is reproduced on stamps, on monuments, on the walls of veterans' halls. And almost no one who has ever looked at that photograph has been told that the rocky hilltop is sitting on the southern rim of a supervolcano that is right now pressurizing faster than almost any other caldera on Earth. The island is now officially called Ioto, a name written with the Japanese characters for sulfur and island, restored in 2007 to reflect the local pronunciation. It sits in the Volcano Islands chain, 1,200 kilometers south of Tokyo. The island itself is 8 kilometers long and 4 kilometers wide, and it is the resurgent dome of a submarine caldera, approximately 9 kilometers across. The defining statistic is the uplift rate. Long-term measurements show the island rising at an average of more than 25 centimeters per year. Short-term spikes have exceeded 1 meter per year. A 2018 study by Akira Ueda and colleagues documented several meters of uplift in a matter of months. The total cumulative uplift since the year 1911 is estimated at over 17 meters, a 5-story building rising out of the sea. Mount Suribachi, the famous flag-raising hill, is 169 meters tall. It sits on the southern rim of the caldera. The last known major eruption was approximately 2,800 years ago, a VEY 6 to 7 event with tephra deposits reaching the Bombon Islands. The Japan Meteorological Agency monitors the island with GPS, tilt meters, and seismographs. Hydrothermal activity is intense. Fumaroles hiss, hot springs steam. The water immediately around the island is stained ochre and rust by iron oxide discharge, visible from satellites in orbit. In 2022, a small phreatic eruption off the southwestern coast produced a brand new island that the sea washed away within months. The wartime landing beaches where American Marines came ashore in 1945 are now stranded as elevated terraces above the modern waterline. The land has lifted in living memory of the veterans who fought there. Today, the only inhabitants are approximately 380 Japan Self-Defense Force personnel. A 2023 paper by Setsuya Nakata and colleagues warned that the rapid uplift signals an actively pressurizing magma body at 2 to 5 kilometers depth. The phreatic eruption mechanism, driven by hydrothermal magmatic interaction, implies that juvenile dacitic magma is close to the surface. The geopolitical sensitivity of an Ioto eruption is its own story. Closure of major Pacific air routes, a potential transoceanic tsunami threatening Tokyo, the Bombon Islands, and the wider Pacific basin. The geophysicist Akimichi Taira has called Ioto, in Japanese language media, the most pressurized caldera on Earth, a phrase widely cited in Japan and almost entirely absent from Western coverage. 3 views once more. The mainstream view treats the long-term uplift as driven by deep magma transfer, with eruption possible within centuries. A second view, the Nakata and Taira position, holds that pressurization is accelerating and that VEI 7 capacity is real. A third view treats the 2022 phreatic eruption as a precursor rather than an isolated incident. From a self-defense force island to the supervolcano that may have ended the Roman world. Number 7. The Ilopango caldera, El Salvador. San Salvador, the capital of El Salvador, is a modern city of more than 2 million people. From almost any high point in the city looking east, you can see a large blue lake set in a ring of green hills 12 kilometers away. The The lake is called Lago de Ilopango. It is one of the largest natural bodies of water in the country. People fish in it, tourists swim in it, children grow up looking at it. And in the year 431 of the Common Era, the basin that holds this lake exploded with a force that may have helped end the classical Roman world. The eruption is named the Tierra Blanca Joven, or White Earth of Youth. It is dated by ice core sulfate signatures and Greenland tephra correlations to 431 of the Common Era, plus or minus 2 years. This refined dating was published by Victoria Smith and colleagues in the Proceedings of the National Academy of Sciences in 2020. The eruption produced between 37 and 84 cubic kilometers of pulverized rock. VE I6 to low VE I7. It was one of the largest volcanic events of the entire Common Era. The early Maya civilization in the Zapotecan Valley was decimated. The Joyer de Seren archaeological site, sometimes called the Pompeii of the Americas, was buried in ash that preserved everything from grain stores to footprints. The atmospheric impact reached the other side of the planet. Stratospheric sulfur injection from Tierra Blanca Joven contributed to what climate historians call the Late Antique Little Ice Age, a multi-decade global cooling event with severe consequences for European and Asian agriculture. Tree ring data from Eurasian conifers shows abrupt growth suppression in the years following 431. Some paleoclimate signals previously attributed to the famous 535 and 536 volcanic event are now being partly returned to Ilopango. A volcano in Central America may have triggered the disruptions that helped collapse the Western Roman world. After the caldera collapsed, post-caldera activity built lava domes inside the lake, the Islas Quemadas, or Burnt Islands. The most recent dome eruption occurred in 1879 and 1880, producing a small lava flow that became briefly visible above the lake surface. Local residents at the time reported that the lake appeared to boil and that fish died in large numbers. The volcano is monitored today by the Salvadoran Ministry of Environment and Natural Resources, MARN, and tracked by the Smithsonian Global Volcanism Program. Hydrothermal activity continues, warm springs along the lake margins, underwater fumaroles, releasing carbon dioxide and hydrogen sulfide. The exposure problem is the central modern fact. The greater San Salvador metropolitan area, with approximately 2.4 million inhabitants, lies directly within the heaviest expected ashfall zone for a future caldera-scale eruption. The bathymetric surveys show the caldera floor sitting 230 meters below the lake surface, with post-caldera collapse pits suggesting ongoing structural adjustment. The Tierra Blanca Joven magma was rhyolitic, viscous, and gas-rich, the textbook recipe for explosive caldera-forming activity. Geophysical surveys indicate a still-present magma chamber at 5 to 10 kilometers depth. Recent seismic swarms beneath the caldera may be signaling magma movement. 3 views run through the literature. The mainstream view treats the long quiescence between caldera-scale events as evidence of low current risk. The Smith and colleagues view, drawing on the refined dating and recurrence interval estimates, suggests we are within the upper bound of the statistical window. A more cautious third view treats the 1879 and 1880 dome eruption as a sign of an active recharge cycle that has not yet ended. From one Central American supervolcano hidden beneath a city, we move to another hidden beneath a tourist paradise. Number 8, the Atitlán caldera, Guatemala. Aldous Huxley once described Lake Atitlán in the Guatemalan highlands as the most beautiful lake in the world. 3 perfectly conical volcanoes rise from its southern shore. Indigenous Mayan villages cluster along the lakeshore in painted houses and woven blankets. Tourists from across Europe and North America come for the kayaking, the coffee tours, the silence at sunrise. The water is sapphire blue, 340 meters deep at its lowest point, fed by no visible river. And the lake basin itself is the throat of one of the largest volcanic eruptions of the past 100,000 years. The caldera measures 18 by 12 kilometers. The defining event is the Los Chocollos eruption, dated to approximately 84,000 years before the present. It produced an estimated 280 cubic kilometers of tephra, VEI7 near the upper end, Tephra from Los Chocollos has been identified in marine sediment cores across the Pacific, the Caribbean, and the Gulf of Mexico, a near-global ash distribution. The Los Chocollos ash is so widespread that it serves as a chronostratigraphic marker for marine geologists working anywhere in the equatorial Pacific. If you pull a sediment core from the floor of the Pacific Ocean, somewhere in the section there is a layer of pale ash that came from a single afternoon in Guatemala 84,000 years ago. After the Caldera collapse, 3 stratovolcanoes built up along the southern rim: Volcan Atitlán, 3,535 meters tall; Volcan Toliman, 3,158 meters; Volcan San Pedro, 3,020 meters. Volcan Atitlán erupted most recently in 1853, with smaller eruptions in 1856 and 1857. It is currently fumarolishly active. The post-caldera magma reservoir feeding these 3 volcanoes is distinct from the original Los Chocollos chamber, but taps the same underlying source. Recent geophysical imaging suggests a renewed magma body developing at depths of 8 to 12 kilometers. The lake itself is hydrologically strange. It has no surface outflow. Water levels fluctuate by meters due to underground drainage and rainfall. Geothermal activity is documented at multiple sites around the shore: San Marcos La Laguna, Santa Cruz La Laguna. The volcano is monitored by INSIVUMEH, the Guatemalan National Institute of Seismology, Volcanology, Meteorology, and Hydrology. Volcano-tectonic earthquake swarms beneath the lake are detected regularly. The 1976 Guatemala earthquake, magnitude 7.5, triggered massive landslides into the lake and killed hundreds along its shoreline, a reminder that the entire region is seismically alive. The reactivation scenario sits at the center of any honest assessment. A VECOEI-7 event would devastate Guatemala City, 50 kilometers east, and Quetzaltenango, 60 kilometers west. The Los Chocollos magma was rhyolitic, with eruption temperatures around 850 degrees Celsius. The Cocos Plate subducts beneath Central America at approximately 7 centimeters per year, generating new magma in the overriding crust. The system is fed, 3 views again. The mainstream view treats the caldera as in long quiescence, with the post-caldera stratovolcanoes as the active surface expression. The emerging view, drawing on recent imaging, suggests a new magma body could herald renewed caldera scale activity. A third view simply notes that the recurrence interval, 84,000 years, places us within the statistical window for a repeat. From the Americas to the Aegean, and the supervolcano Greek myth literally trapped a giant beneath. Number 9. The Kos-Nisyros caldera, in the Aegean Sea, Greece. In Greek mythology, the Olympian gods fought a war against the giants called the Gigantomachy. One of the giants was Polyvodus. Poseidon, the god of the sea, broke off a piece of the island of Kos and hurled it at Polyvodus, crushing him beneath. The piece of land became the island of Nisyros. The giant's groans, trapped beneath the rock, are what the islanders today call the rumbling of the volcano. It is a remarkable myth because the geology underneath it is also remarkable. Kos-Nisyros is a submarine and partly subaerial volcanic system in the southeastern Aegean between the Greek islands of Kos and Nisyros, and it is one of the largest dormant supervolcanoes in the eastern Mediterranean. The complex includes 6 islands: Kos, Nisyros, Yali, Strongy-Li, Pergusa, and Pachia, all of which are remnants or peripheral features of a much larger system. The defining event is the Kos Plateau Tuff eruption, sometimes called the Kos Ignimbrite, dated to approximately 161,000 years ago. The volume is estimated between 60 and 100 cubic kilometers. VERI-7. It was the largest known volcanic event in the eastern Mediterranean during the entire Quaternary period. The deposit covers Kos, parts of Nisyros, and reaches the Bodrum Peninsula on the Turkish coast. The eruption was first comprehensively described by the German volcanologist Hans Ulrich Schminke in the 1970s, with refined dating by Jenny Allen and colleagues in 1999 and 2005. Nisyros itself, the smaller modern island, is a younger post-caldera stratovolcano built on the southern rim of the larger system. It last erupted phreatically in 1888, creating the Stephanos crater, which today is a steaming, sulfur-stained pit on the floor of Nisyros' caldera. Tourists routinely descend into the crater on guided walks. The fumaroles inside it reach surface temperatures over 100 degrees Celsius and emit carbon dioxide, sulfur dioxide, and hydrogen sulfide. Major unrest occurred between 1996 and 1998. Thousands of seismic events. Ground deformation up to 14 centimeters of uplift. Increased fumarole temperatures. The unrest is thought to have been driven by magma intrusion at shallow depth, though no eruption ensued. The system was recharged, pressurized, and then subsided again. The National Observatory of Athens monitors the system today with seismic GPS and gas chemistry stations distributed across the islands. Kos has a permanent population of approximately 33,000 and a summer population that swells over 100,000. The smaller island of Yali is mined commercially for pumice and perlite, products of the same supervolcano exported globally for construction and horticulture. The Kos Plateau tuff magma was rhyolitic and gas-rich. The geochemists Olivier Bachmann and George Bergantz have used it as a reference standard for caldera-forming magmas in their broader theoretical work on crystal mush systems. Submarine bathymetric surveys have revealed multiple post-caldera collapse features and a complex network of resurgent domes. A 2020 paper by Emma Tomlinson and colleagues identified Kos-Nisyros as a top-tier candidate for a future Mediterranean super eruption, ranked behind only Campi Flegrei and Santorini. A modern caldera-scale eruption would devastate Kos and the Bodrum coast of Turkey, generate Mediterranean tsunamis, and disrupt European air travel for weeks. Three views close the section. The mainstream view treats Kos-Nisyros as in long quiescence with low decadal probability. The Tomlinson view places it third in the Mediterranean threat ranking, with an active subsystem that warrants closer monitoring. A third view treats the 1996 and 1998 episode as the start of a recharge phase that requires far closer monitoring over the coming decades. From the Aegean back to North America, and the most carefully watched supervolcano on the continent. Number 10. The Long Valley Caldera, California, United States. In eastern California, on the eastern flank of the Sierra Nevada, there is a ski resort called Mammoth Mountain. Skiers come from across the western United States in winter, hikers come in summer. The town of Mammoth Lakes, with about 8,000 permanent residents and millions of annual visitors, sits at the mountain's foot. Mammoth Mountain itself is a post-caldera lava dome complex. It sits on the southwestern rim of the Long Valley Caldera, a 32 by 17 kilometer depression in the High Sierra, among the largest quaternary calderas in North America. 760,000 years ago, this caldera produced the Bishop Tuff eruption, approximately 600 cubic kilometers of pyroclastic material, VEI7. Tephra from the Bishop Tuff has been identified across the western United States from California to Nebraska, a continental-scale ash blanket. The American volcanologist Wes Hildreth's foundational work on the Bishop Tuff established the textbook model for how caldera-forming magma chambers behave. His monographs are still required reading for anyone studying these systems. In 1980, the caldera awoke. 4 magnitude 6 earthquakes struck the area within 48 hours. Resurgent dome uplift since that year has totaled approximately 80 centimeters at the center of the caldera. The volcano has been continuously restless ever since. The United States Geological Survey monitors it through the California Volcano Observatory with seismic networks, GPS, gas chemistry, and tilt instruments providing continuous data. Annual volcano-tectonic earthquake counts regularly exceed 600 events. Periodic swarms produce thousands of micro-earthquakes in days. In 1989, an unusual phenomenon began on the flanks of Mammoth Mountain. Trees started dying in clusters. Approximately 100 acres of forest were eventually killed. The cause was magmatic carbon dioxide leaking through the soil and suffocating tree roots. The CO2 tree kill zone became a teaching case for volcanic gas hazards and is still a marked feature on park maps. Hot Creek and Hot Bubbling Pool, popular recreational destinations, are surface expressions of the same geothermal system. The Casa Diablo geothermal power plant generates approximately 40 megawatts of electricity from caldera heat. The most recent eruptive activity in the broader Long Valley region was at the Mono Inyo Craters Chain, a series of small eruptions between 250 and 600 years ago, well within the Holocene. The USGS's National Volcanic Threat Assessment classifies Long Valley as a very high-threat volcano, alongside Yellowstone and Mount St. Helens. A 2023 paper by Patrick Welly and colleagues used INSAR to detect new uplift episodes that began in 2021, suggesting renewed magma input at depth. The Long Valley Hydrologic Advisory Committee was established specifically to monitor groundwater and gas systems for eruption precursors. The reactivation scenario is sobering. A Bishop Tuff scale eruption would devastate the western United States. North American aviation would be paralyzed. The stratospheric sulfur injection would produce years of measurable global cooling. Three views run through the modern monitoring literature. The mainstream view treats Long Valley as in long-term recharge, but unlikely to erupt at Caldera scale within centuries. The Hildreth-derived view holds that the magma chamber is persistently capable of being retapped, and that smaller eruptions are far more likely than Caldera-scale ones, but that smaller still means catastrophic. A third view treats the 1980 swarms and the 2021 uplift episode as together, marking a multi-decade reactivation, with hazardous eruption possible within a human generation. The Dean of Long Valley Research, Roy Bailey of the USGS, called this caldera the most carefully watched sleeping giant in North America. The question is what the watchers will see when the giant wakes. 10 supervolcanoes. 10 places that should be famous and are not. The line that separates them from the extinct giants of geological history is the line between magma chambers that still exist and magma chambers that have finally cooled. A volcano is classified extinct when no magma chamber remains and no plate tectonic supply is plausible. Dormant means the opposite. Magma chamber persists. Supply pathway is intact. Eruption is geologically possible. The scientific tools that draw this line are recent. Satellite radar interferometry, or INSAR, can detect ground motion at the centimeter scale across continents, and was used by Pritchard and Simons in 2002 to reveal which Andean systems were still alive. Seismic tomography can image magma bodies as low-velocity zones beneath calderas. Gas chemistry signatures, carbon dioxide flux, helium-3 to helium-4 ratios, sulfur dioxide emissions can identify mantle-derived magma at depth. The Altiplano Puna magma body beneath the Andes is the type example of a continental-scale crustal magma reservoir, estimated at 500,000 cubic kilometers of partially molten rock. A magma chamber can be drained and refilled multiple times across a million years, so long as the supply pathway from the mantle remains open. Recurrence intervals, calculated from the dating of past eruptions, give us probability estimates. The conditional probability problem is what makes these estimates so unsettling. Low decadal probabilities multiplied by civilization-scale consequences produce expected losses that dwarf almost every other natural hazard. The Hunga Tonga lesson of 2022 cannot be overstated. A submarine volcano produced an eruption that was, by some measures, the most powerful in modern instrumental records, with very limited precursor warning. Submarine systems can detonate. The shift in scientific framing over the past 3 decades from supervolcano as a sensational media term to supervolcano as a formal class of V, EI, 7, and larger systems reflects how seriously professional volcanology now takes this category. The contrast with truly extinct giants is instructive. La Garita in Colorado produced the Fish Canyon Tuff eruption 28 million years ago, the largest known volcanic event in Earth's history. La Garita is dead. The magma supply has shut down. The chamber has solidified. Cerro Galán in Argentina is similar. These are the geological memory of what the dormant systems we have looked at could one day do again. The ambiguous middle ground, systems like Cerro Blanco that may be cooling or may be in recharge, is where most of the modern uncertainty sits. The climate stakes of a single super eruption are not abstract. The Tambore eruption in 1815 in present-day Indonesia produced the year without a summer. 1816 brought global cooling of approximately 0.5 degrees Celsius. Crops failed across Europe and North America. Famine followed. Social unrest followed the famine. The Pinatubo eruption in 1991, a smaller VEI6 event, produced cooling of approximately 0.4 degrees and validated the mechanism by which stratospheric sulfur produces this forcing. Sulfur dioxide injected at high altitude is converted to sulfate aerosols that reflect incoming solar radiation back to space. Aerosol residence time in the stratosphere is 1 to 3 years. Heterogeneous chemistry on aerosol surfaces destroys stratospheric ozone, with secondary consequences for ultraviolet radiation at the surface. The Toba super eruption, approximately 74,000 years ago, has been associated with what the American anthropologist Stanley Ambrose proposed as the bottleneck hypothesis, a moment when the human population may have been reduced to between 1,000 and 10,000 individuals worldwide. Ambrose's hypothesis is contested. Stone Age tool layers above and below the Toba ash at the Jwalapuram site in India suggest cultural continuity rather than collapse. The bottleneck remains an open question. The 535 and 536 volcanic event produced simultaneous crop failures across Europe and Asia, plague outbreaks, and civilizational disruption, and is now, with the refined dating of Tierra Blanca Joven, partly attributed to Ilopango as well. The late antique Little Ice Age was a multi-decade phenomenon driven, at least in part, by stratospheric sulfur from a sequence of eruptions. Modern agricultural exposure compounds the problem. Industrial monocultures with low diversity have low resilience to multi-year cooling. The phosphate fertilizer supply chain depends on the transport of mineral nutrients across regions sensitive to stratospheric chemistry changes. The aviation consequence is its own category. The Eyjafjallajökull eruption in 2010, a VEI4 event, cost the global aviation industry approximately $1.7 billion in 5 days of European airspace closure. A VEI7 ash cloud disruption would last months and span continents. The Food System Fragility Study by Mani and colleagues in 2021 estimated that a modern Viro VEI7 eruption could trigger global famine within 2 years. The reinsurance industry's catastrophe models treat the largest dormant supervolcanoes as the largest tail risks on the global hazard landscape. The monitoring gap is the operational question. The premier volcano observatories, the United States Geological Survey, the Italian National Institute of Geophysics and Volcanology, the Japan Meteorological Agency, the Philippine Institute of Volcanology and Seismology, are funded and capable. The Smithsonian Global Volcanism Program maintains the global catalog, but coverage is highly uneven. Yellowstone, Long Valley, Compifligre, Ira, and Taupo are well monitored because they have been famous long enough to attract sustained funding. Kikai, Macolod de Bombon, Atitlán, Ilopango, and Kos-Nisyros are under-monitored relative to their threat. Cerro Blanco, Aniakchak, La Pequeña, and Cerro Galán are barely monitored at all. The funding follows public attention rather than threat ranking. A single major caldera with continuous instrumentation costs $1 to $5 million per year to monitor. The total USGS volcano hazards budget is approximately $30 million per year for the entire United States, less than the cost of a single F-35 fighter jet. The Aleutian Arc has more active volcanoes than any region on Earth and fewer instruments per volcano than Italy. The submarine monitoring problem is even harder. Ocean bottom seismometers and gas sensors are expensive, hard to maintain, and have short operational lifetimes. The Kobe University work on Kikai is a model for what dedicated submarine monitoring requires, and it is not being replicated anywhere else at the scale the global threat would justify. There is no international body equivalent to the World Meteorological Organization for volcanic risk. The volcanic ash advisory centers exist for aviation safety but not for ground hazards. The forecasting horizon ranges from hours to days for VEI 3 to 4 events, weeks to months for VEI 5 to 6, and is deeply uncertain for VEI 7. What we still do not know is the next layer of honesty. The fundamental question, what triggers a VEI I7 eruption from a long quiet system, remains open. The crystal mush model developed by Olivier Bachmann and George Bergantz holds that most caldera magma chambers spend most of their lives as crystal-rich slurries that cannot erupt. Reawakening requires a thermal recharge from new magma input, or a tectonic stress release or volatile saturation, or some combination of all three. The precursor question whether there are always warning signals or whether some systems can fail without warning is unresolved. The magma volume question, how much eruptible material exists in the modern Yellowstone, Long Valley, or Kikai chambers, has different answers in different studies. The Yellowstone consensus is that most of the chamber is crystal mush and that the eruptible volume is far smaller than the total reservoir. The Kikai dilemma is that an actively growing dome on the seafloor is unambiguous evidence of eruptible magma at the surface today. The dating question, how many Holocene active supervolcanoes are actually in their final extinction phase, has no clear answer. Cerro Blanco's subsidence may be that signature for one specific case. The submarine question, how to monitor systems we cannot easily reach, is the operational bottleneck of the field. The Marsilli Seamount in the Tyrrhenian Sea is Europe's largest volcano and was only fully characterized in the past 2 decades. The Mount Erebus province in Antarctica and the possibility of sub-ice supervolcanic systems remains underexplored. The deep time recurrence question, whether every EI7 events are truly random in time or arrive in clusters, has different proponents on different sides. The eruption rate hypothesis holds that long quiescence reduces magma chamber readiness. The opposite hypothesis holds that long quiescence allows pressure to accumulate. Machine learning applied to seismic and gas data has produced mixed results. The Cambridge volcanologist Steve Sparks and his colleague Catherine Cashman have argued in print that fundamental gaps remain in our understanding of caldera trigger mechanisms. 10 supervolcanoes capable of erupting again, and most viewers had heard of perhaps 1 or 2 before this video. The civilizations that have risen and fallen since the last super eruption is a measure of how rare these events truly are. AVEI7 eruption somewhere on Earth has, integrated across all known dormant systems, a probability of roughly 1 in 1,000 per year. That translates to a roughly 1 in 10 chance across a long human lifetime. The geographic reframe is what makes the topic personal. Most of these systems sit beneath someone's holiday photographs. Atitlán, Ngorongoro, Crater Lake, Lake Ilopango, these are calderas as ecosystems and cultural landscapes, not as catastrophes in waiting. The infrastructure dependency is its own category. Casa Diablo in California, Tiwi and Macbon in Luzon, geothermal plants across Iceland and New Zealand, power generation built on caldera heat. Naples sits inside Campi Flegrei. San Salvador sits below Ilopango. Manila sits beside the Macolod corridor. 3 cities of millions, each living above or beside a supervolcanic system. The civilizational pattern is consistent across continents. Humans build on and around volcanoes because the soils are fertile, the hot springs comfortable, the landscapes beautiful. Every continent has hosted multiple super eruptions across the Pleistocene. The contrast with extinct giants, La Garita, the truly silent Kerguelen, the cold magma chambers of the deep past, gives us our reference for what the active systems are still capable of doing. The resilience question, what surviving a super eruption would require of modern food systems, is being studied seriously by a small number of researchers and almost no one in the wider policy community. This is the era when humans first know what supervolcanoes are. Our ancestors only ever saw the aftermath. The Akahoya event 7,300 years ago was experienced by Jomon people in Kyushu who had no concept of what had killed their cousins 100 kilometers away. The Tierra Blanca Jovan eruption of 431 was experienced by Maya farmers who could not have imagined the global climate consequences they were helping to set in motion. We can imagine those consequences now. We can model them. We can monitor the systems most likely to produce them. The agency framing is the closing point. Knowledge of a dormant supervolcano is the precondition for any meaningful response to it. The scientists named throughout this video, Yoshiyuki Tatsumi, Victoria Smith, Wes Hildreth, Roy Bailey, Matthew Pritchard, Hans Ulrich Schminke, Walter Baez, Setsuya Nakata, Giovanni Orsi, Renato Solidum, spend their working lives watching what most of us have never noticed. Return for a moment to the photograph. 6 Marines, a flagpole, a rocky hilltop in the Pacific. The ground beneath them rising at a meter a year. The caldera floor pressurizing. The fumaroles staining the sea ochre. Mount Suribachi, less than 200 meters tall, sitting on the rim of something approximately 9 kilometers across. We've all been standing on the rim of something the whole time. Some of these systems may never erupt again in human time. Others may erupt this century. The truth is that we do not know which is which. What we choose to watch and what we let slip beneath the waves will shape the answer.